Okay, so what we are trying to calculate. We have the initial state, we have the evolution operator, we have the final state. And this S matrix element, we could relate it to some time-ordered product exponentials, etc. And then we said that, okay, the initial and final state, I can write it in terms of some annihilation creation operators. And so eventually I will end up having some operators of this form, A1 at the time infinity, A2 at the time infinity, A3 at the time, no, let's say AN at the time infinity. These are basically my final state. And then I have A1 dagger at the time minus infinity, A2 dagger at the time minus infinity. N plus 1, N plus 2, N plus M. This omega is the minimum energy configuration. It doesn't have to be empty, but most of the time we will take it to be empty.
This just happened. The annihilation creation operators just became time dependent.
Okay, so
time dependent.
I am now in the Schrödinger picture, Heisenberg picture.
Oh, they evolve, alright.
So operators are the ones that are evolving. And, okay, this is what I would like to calculate. A1, A2, they can be different fields, correspond to different fields. There's no problem with that. Well, they are already kind of time ordered. This is also kind of nice, but I will end up having, I want to relate this this matrix element to this one. Why? Because it will be easier to work with that time-ordered products. That will be my aim first, because once I relate this matrix element in turn to these matrix elements somehow, then we will start developing the machinery to study those time-ordered products. Now the fields phi, I can write it as d cubed k divided by 2 pi cubed, 1 over square root of 2 omega k. These were the usual integrals and the normalization. Then I have ak e to power minus I kx plus, if you like, bk dagger e to power I kx. B can be a, it can be different, it won't really matter for me. This is my phi. Well, if this was a non-interacting theory, all the time dependence will be in the kx factors, where k0 is omega k. If this is the full theory, full interacting theory, then these ak operators will also have some time dependence. Yeah, there will be the evolution due to h0, which I include in the exponent. These AKT operators, they will depend on time only due to V. This is not the interaction picture. Remember, in the interaction picture, we also separated the time dependence. Time evolution due to H0 was in the operators. Time evolution due to V was in the potential. Now here I'm making a similar separation of time dependences. Time dependence due to H0 is included in the exponent. time-dependent evolution due to V is in the operators, AK and AK dagger, BK dagger. And I will also make the assumption that V is 0 at minus infinity. So I have at minus infinity, there's no interaction, no potential. But at a very early time, I turn on the interaction. At a very late time, I turn off the interaction so that at t equal to plus infinity, still there's no interaction. So what I know is AK of t, and similarly for BK of t, is time independent as t goes to plus or minus infinity. Basically, time derivative of AK will be equal to the time derivative of BK, well, in general they are not equal. Both will go to 0 as t goes to plus or minus infinity. This is another assumption I'm making. Well, at very early times, they are not in particle. There is no interaction. At very late times, there are no interactions. Somewhere in between, there are some interactions. Now, let me consider this thing. I'm taking my field, applying the Klein-Gordon operator to my field, and taking the Fourier transform. If this were a non-interacting theory, phi will satisfy the Klein-Gordon equation. That would have been 0. Well, in the interacting theory also, you can just think of it in this way. In the interacting theory, at very late times or very early times, my field will satisfy almost the Schrödinger equation, let's say. So that will give me 0 unless there is a 1 over p, in momentum space. If you take the momentum space, this is minus p squared plus m squared, multiplying whatever expression I have. The only term that will contribute will be the term that depends on 1 over p squared minus m squared. This is my propagator. This is what we will be actually doing. So why do I study that term? Basically, to be able to pick up the pole corresponding to this one. Now, how will that work? Well, let's say, let me take the 4-dimensional Fourier transform. Sorry. Which will be d for x e to the power I p x. Let me write that operator explicitly. And my field, you see, my field is not going to 0 at t is equal to plus or minus infinity. They will be my annihilation creation operators. That's what I'm looking for. In fact, I would like to somehow relate this integral to my annihilation and creation operators at infinities. That will be my purpose. But at x is equal to infinities, I can assume that they go to 0. Because at very far away distances, I don't have any particles. My particles is somewhere over here. At very early times, my particles exist. At very late times, my particles should exist. Those are the times when I'm creating my particles and annihilating my particles, observing my particles. So they exist at t goes to minus infinity and t goes to plus infinity, but they don't exist at very far away distances. Outside Earth, let's say, my particles are not there. They are here in my lab. That is why I will assume phi goes to 0 as r goes to 0, which basically allows me to take integration by parts, which will give me, I can get rid of this Laplacian by doing integration by parts, that will be d4x e to power, well, let me also introduce the I here, IPX del t squared plus p squared plus m squared phi d4x e to power I px I del t squared plus I omega p squared. I just didn't do much yet. Well, let me add and subtract. Why did I do that? Well, I'm basically trying to convert that integrand into a total derivative in time. This will be d4x e to power I px, let's see, dt, I dt plus omega p, and plus I omega p, I dt plus omega p. Now this is the kind of the trick. You see, this derivative can act on everything over here, multiplied by the exponent. That will be one contribution. The other contribution will be that derivative acts on this one, bringing down a factor of I omega p. P0 is omega p. And the rest just remains as it is. So now the trick is already over here. You see, I have a d4x integral. There's an integral over t over there. So if I integrate over the t, I will get whatever that space integral is at t is equal to plus infinity and at t is equal to minus infinity. I'm almost done. So let's see what that expression is. This will be equal to dt, time derivative, times d cubed r e to power I omega pt minus I p r I dt plus omega p. Well, my phi field, I had already written down its expression, d cubed k divided by 2 pi cubed 1 over twice square root of twice omega k a k e to power minus I kx plus bk dagger e to power I kx. And these operators depend on time t. And keep in mind that eventually I'm only interested in that space integral for t goes to plus or minus infinity. In those limits, ak of t and bk of t, they don't depend on time. So now I will be taking this time derivative over there. So I can just ignore the time dependence of ak and bk, which will give me, okay, dt, del t, e to power I omega p of t, d cubed r e to power minus I p dot r, d cubed k divided by 2 pi cubed 1 over square root of 2 omega k. I'm not taking the time derivative of ak, so the first term is ak of t times omega k plus omega p plus bk dagger of t omega p minus omega k of t and then I have these exponents. Now I will evaluate the R integrals. The space integral, well, the space integrals will basically give me Dirac delta functions. This three-dimensional Dirac delta of P minus K, and then plus Bk of dagger of T, omega P minus omega K, e to power I omega K of T, 2 pi cubed, P plus K. Well, both Dirac delta functions tell me that P and K should have the same magnitude, and hence omega P and omega K should be equal. Well, if omega P and omega K are equal, then the second term just doesn't contribute. I have omega P minus omega K, which will become 0. And now I can evaluate the K integral. The K integral will give me, well, 2 pi cubes cancel, 1 over 2 omega K. There is omega K plus omega, well, P is equal to K now, omega K, AP of T, e to the power minus I omega P of T. Now I evaluated the K integral. Well, these exponents, they will cancel each other. Now this is under the square root, and I am left with dt from minus infinity to infinity, the derivative of square root of 2 omega K a K of T, which gives me square root of 2 omega K, a K at infinity minus a K of 0. A K of minus infinity. So what did I obtain? Whatever my field is, whatever phi is, it can be any particle. In fact, it doesn't even have to be a single field. It can be a composite operator which creates two particles at the same time, like an operator that creates, I don't know, the hydrogen atom. Phi can even be such a field, creating more than one particles at the same time. And this will be basically square root of 2 omega K, a K infinity minus, no, sorry, this is K. I made the mistake. K was the field integral. P is my free momentum. This is P. You see, I'm integrating over K here using the Dirac deltas. So here, Dirac deltas basically tell me that K should be replaced by P. So this is my result. Now remember what I was trying to calculate. I'm trying to calculate This is what I'm trying to calculate. Well, let me just make a small change. Well, you see, it is under time ordered product. The only thing I did was I replaced a1 of infinity with a1 of infinity minus a1 at minus infinity. I'm basically adding a term over there. But keep in mind that this is inside the time ordered product. The terms I added contains an annihilation operator at minus infinity. But annihilation operators at minus infinity, when acting on the vacuum, it will give me 0. So I basically added 0 here. Well, I can basically do the same thing for all the annihilation operators. Now, there is one crucial thing, let's say, if you would repeat the same derivation, exactly the same derivation, but with the opposite sign in the exponent. This would have been it would have just given me the creation operators. So I can pick up in this expansion of the field. Where's the field? Okay, in this expansion of my field over here, I can pick up the annihilation operator by acting on this field with my Klein-Gordon operator and multiplying it with e to the power I px and integrating over all x, Fourier transforming. Or I can pick up the other operator by multiplying it with e to the power minus I px and doing all the tricks. Now the main difference will be due to the sign change. Here you would get I dt minus omega p terms probably. So the a terms will cancel, the b dagger terms will remain, so you will end up having, instead of the annihilation operators in the field, you will extract the creation operators in the field. So that basically almost completes my proof, because you see now what I will do. For these terms, I will have I d4 x e to the power I p x1, p1 x1, delta 1 plus m1 squared, I d4 xn e to the power I p n xn, delta n plus mn squared. Then I will have d4 xn plus 1 e to the power minus I p n plus 1 xn plus 1 Klein-Gordon operator. This one acting on the time-ordered product of phi of x1, phi 1 of x1, phi 2 of x2, phi n plus m at xn plus m. This is called the LSZ reduction formula. So that kind of completes what I wanted to do. You see, I remembered I started with the S matrix element. I can write this in terms of annihilation creation operators. But or the time ordered product of them, because they are already time ordered. What I wanted to do was write these annihilation creation operators in terms of the fields I have. And that's what I did. So I can write This is nothing but an S matrix element. The S matrix elements for so-called n plus m particles, n particles scattering into m particles, it's enough to calculate this matrix element. So if I can calculate that matrix element, then by just applying this operation to that matrix element, I obtain my S matrix. This is the so-called, since there are n plus m fields there, it's called an n plus m point function. There are n plus m different points in that expression. Now let's do one application of this. Just a single particle. In the non-interacting theory, in fact. There are no interactions. Let me also consider just the real scalar field. So this is what I would like to calculate. Now later on, all the n-point functions will in fact be written in terms of this 2-point function. This is so-called the Feynman propagator. Well, I know what these phi's are. Phi 0 of x is d cubed k divided by 2 pi cubed, 1 over square root of 2 omega k, a k e to power minus I kx plus a k dagger e to power I kx. This is my field. It's in the Schrodinger picture or the interaction picture, whichever one you want, because since there are no potentials, here the Heisenberg picture and the interaction picture, they are basically the same. So what I'm trying to calculate is this one. d4k divided by 2 pi cubed, 1 over 2 omega k 1, d4k 2 divided by 2 pi cubed, 1 over square root of 2 omega k 2, theta x1 0 minus x2 0. I'm just using the definition of the time ordered product of a k1 e to power minus I k1 x1 plus a k dagger e to power I k1 x1 times the other one plus, well, if x2 is at a later time, just change their order. So this is what I need to calculate. So this is D4K1. And of course it's between vacuum and vacuum. Okay, what kind of matrix elements do I have? Let's see, here I have a vacuum. The annihilation operator acting on the vacuum bra, it will give me 0. So there's no contribution from this term. And similarly, I have the annihilation operator over there. It is acting on the vacuum from the left. There is no contribution from that one. Similarly, this term over here will not contribute. It will annihilate the state on the left. And so as this one, this will annihilate the state on the right. So these are just 0. And what I am left with is D4K1, D4K2. No, sorry, these are D cubed K1 and K2. Divided by 2 pi to the 6 twice omega K1 twice omega K2 theta x1 0 minus x2 0 of AK1 AK2 dagger e to power minus I K1 x1 plus I K2 x2, and then I have plus theta x2 0 minus x1 0 AK2 AK1 dagger, this is 1, of e to power minus I K2 x2 plus I K1 x1. Again, these are the vacuum matrix elements. Now, what else do I know? I know that AK1, AK2 dagger, this vacuum matrix element, will be equal to the commutator plus AK2 dagger AK1. I just use the definition of the commutator, nothing else. Now, this operator just annihilates the vacuum, so there is no contribution from that one. And this is just 2 pi cubed Dirac delta K1 minus K2. Well, it will be the same for both of the operators. So what I will end up having is, let me evaluate the K2 integral. There will be only a K1 integral. 1 over twice omega K1. And then I will have theta x1 0 minus x2 0 e to power minus I K1 x1 plus I K2 x2 plus theta x2 0 minus x1 0 e to power minus I K2 x2 plus I K1 x1. Well, let me write those exponents also explicitly. If you see a mistake, please let me know.
K1 and K2 should be in the exponentials.
Which ones?
Qx.
K, yes, K1 and K2 will be the same, sorry. So I will have e to power minus I omega 1 minus omega 2, no. Omega 1, yeah. K1 x1 minus x2, because when the three components are the same, the zeroth component are also the same, and e to power I k1 x1 minus x2. Are the exponents correct? Yeah. Okay. So let me write the exponents explicitly. E to power minus I omega let me just use k. Omega k x1 0 minus x2 0 plus I k dot delta r r1 minus r2 theta x2 0 minus x1 0 e to power I omega k x1 0 minus x2 0 minus I k dot r1 minus r2. Now I will do another trick, d cubed k divided by 2 pi cubed, 1 over 2 omega k. I will leave the first term as it is. In the second term, I will change k to minus k. Omega k doesn't change. What do I gain by this is the space parts of the exponents are now equal. I mean, in this term, or in this term, I replace k by minus k everywhere. The integral measure doesn't change, omega k doesn't change. The only thing that changes is the second term in the exponent. So that second term in the exponent becomes the same as the second term in the first exponent. So now I can take them out of the parentheses. Now let me even write that slightly differently. Let me just use r and t. R will be r1 minus r2. T will be x1 0 minus x2 0, just a shorthand notation. So I will have e to power I k dot r theta x theta t e to power minus I, now this is plus I by the way, minus I omega t divided by omega plus omega k plus e to power minus I omega t theta of minus t divided by omega minus omega k. The first term I will evaluate it at omega is equal to omega k. The second term I will evaluate it at omega is equal to minus omega k. If it doesn't remind you of anything yet, let me write it let me just slightly change it. Theta of t, omega minus omega k e to power minus I omega t divided by omega squared minus omega k squared, evaluate that omega is equal to omega k, and minus e to power minus I omega t divided by omega plus omega k divided by omega squared minus omega k squared e to power minus I omega t, evaluate that omega is equal to minus omega k. So in both terms I have this term. I'm just multiplying it with omega minus plus or minus omega k, and then taking the limit as omega goes to plus or minus omega k. But this is nothing but the residue of e to power minus I omega t divided by omega squared minus omega h squared at omega is equal to plus minus omega k. So I can actually use contour integration. So let me imagine a contour. Let's say this is the integration variable. I will call it k0. I'm just giving it some name. And I should have a residue 1 at omega is equal to omega k. Let me first look at this exponent. If t is positive, I should close this contour from below. Right? If t is positive, omega should have a negative imaginary part so that the contour at infinity will not contribute. And if t is negative, no, if t is positive, I should close it from below. And the residue at omega is equal to omega k should be within my contour. So this is one of the poles that I should have. This is omega k. No, sorry, I'm integrating over omega. Not k0. I will be integrating over omega. That's why I call this omega. And the other pole should be over here at minus omega. No. At minus omega k. So if I shift my poles like in this form, when I'm integrating e to power minus I omega t divided by omega squared minus omega h squared, omega k squared, if I shift my poles in that way, now if t is positive, I close the contour from below, lower complex plane. I contain the residue at omega k. This is the residue at omega k. If t is negative, I should close the contour from the upper complex plane. So I contain the residue at minus omega k, so it is this one. This is the residue at minus omega k. So this is what I can do now. This was the integral I'm trying to evaluate. That is d cubed k divided by 2 pi cubed is this one. I have e to power ikr, k dot r. Now the remaining part is nothing but d omega divided by 2 pi I. Remember, the contour integral will give me, the Cauchy residue theorem will give me a 2 pi I times the sum of the residues, e to power minus I omega t divided by omega squared minus, well, let's see, omega k minus I epsilon squared. So the poles are at omega is equal to plus or minus omega k minus I epsilon. That is how I shifted my poles. Now let me again make another change of variable. Let me call omega k0, just for convention. And then I have d cubed k dk0 integral. I will just denote it by d4k, the four-dimensional integral. I have d4k divided by 2 pi cubed, e to power minus I kr, kx. This is the four-dimensional scalar product. 1 over omega squared minus omega k squared plus 2i, let me call this epsilon prime. 2i epsilon prime omega k. Then, of course, there is the epsilon prime squared term, which I ignore. Epsilon is small. But if epsilon prime is sufficiently small, epsilon prime times omega k is also small. Eventually, it will go to 0. So I can call all of this thing as I epsilon. Two pi cubed, e to power minus I kx divided by omega squared. Now, omega is now k, k0. This is k0 squared minus k squared minus m squared plus I epsilon. Well, this is nothing but 4 vector k squared. And hence this integral is, there is a minus I here, minus I d4k divided by 2 pi to the 4. Remember, there is another 2 pi I here. I becomes minus I. 2 pi makes this 2 pi 4. E to power minus I kx divided by k squared minus m squared plus I epsilon. Okay, so this is called the Feynman propagator. At least this is one way of deriving the Feynman propagator. Well, let me just sketch another way of deriving exactly the same Feynman propagator. You see, what we are calculating is this time-ordered product. And remember that phi satisfies this equation. Let me see what this propagator satisfies. Let me just act it on one. Well, that will be 0 time-ordered product of x1, phi 0 of x2. If this was the only term, then this would be 0. This is 0. But this is not the only term. Remember, the problem is delta 1 squared is del T1 squared minus the Laplacian. Time ordered product of phi 1, phi 2 is equal to step function t1 minus t2, phi 1, phi 2, plus the step function t2 minus t1, phi 2, phi 1. Now, if I take the time derivative of this time ordered product, okay, there is the time derivative of the field itself. But then there is the time derivative of the step functions. Well, time derivative of the step function is a Dirac delta function. So this time derivative of the time ordered product will be time ordered product of the derivative of the field, but then I will get Dirac delta T1 minus T2, the commutators of phi 1 and phi 2. If I take the time derivative once more, well, I will get several terms. I will get this one, the time derivative of my field, plus I will get the Dirac delta function and the commutator of these two fields, phi 1 and phi 2. And then I will get some more terms from the second term, this one. But remember, that term is 0. Phi 1 and phi 2 are the same field at different, the commutator of the same field at equal times, but field commutes with itself. So this is 0. There is no contribution from this one. This is, well, the time derivative of the field in the scalar theory is the momentum. And the momentum commutation with the field is the three-dimensional Dirac delta. So the second time derivative of this time-ordered product is equal to the time-ordered product of the second derivative and the second derivative of my field plus the four-dimensional Dirac delta. But that tells me that my propagator satisfies this equation. The four-dimensional well, when I act on it with the Klein-Gordon operator, I get the four-dimensional Dirac delta, which basically tells me that this is the Green's function. Well, you see, if you go back to our solution, well, there are all these factors of I, which I didn't write over here. If you go back to our solution over here, if you act on this with the Klein-Gordon operator, you will get k squared minus m squared inside the integral, canceling the denominator. What remains will be a four-dimensional Dirac delta. And in fact, what our reduction formula, Lehmann-Manzi, the reduction formula does is it just picks up the pole of this term. If such a propagator appears in our matrix element, it will just pick up the contribution of the pole. When k squared is equal to m squared, that's when the particle is on shell. That is for my asymptotic states, which it will not pick up the virtual particles, but the real particles at the external legs. So any last question before you go?
Phi 1 and phi 2 are two different fields, right? That's
No,
why...
no. phi 1 is phi of x1, phi 2 is phi of x2. Just the same field at different points. I was just too lazy to write phi 1 and phi 2. You see here. This is what I denote as phi 1. This is what I denote as phi 2 in the successive computation.
If there were two different fields, then the commutator of them still zero, right? Or
the fields commute with itself. The thing that doesn't commute is a field with the corresponding conjugate momentum. That commutation is non-zero. So see you next week.
next month.
Next Monday.